Welcome everyone to our next DSG seminar. I'd like to start as usual by thanking SAP for sponsoring this seminar series. It's my great pleasure to introduce our speaker, Peter Boncz. Peter is a tenured researcher at CWI, which is a National Research Institute in Mathematics and Computer Science in Netherlands. He's also a professor at the VU University at Amsterdam. Peter is one of the most impactful and well-known systems researchers in the field of database management systems. He pioneered and made significant contributions to several areas in the field, including column-oriented research, relational database management systems, and vectorized query processing. His PhD thesis led to the development of MonadDB, which is still one of the most popular open source column-oriented relational systems. Later on, he was the chief architect of data distilleries, which produced data mining software on top of MonadDB and was successfully acquired by SPSS, which is now part of IBM. He then co-founded Vectorwise, a new column-oriented relational system that pioneered and popularized vectorized query execution, which was later successfully acquired by Actian, which is the company that commercializes the Ingress system. So I can't list all systems he had contributed to, but most lately he also co-founded, along with Thomas Neumann, and advised Celerata, which commercialized the Hyper system. He's also advised many excellent PhD students, such as Marcin Zukowski, who co-founded Vectorwise and later Snowflake. His contributions has been recognized by many awards. He was given the Dutch ICT Regi Award in 2006 for his role in data distilleries, a 2009 VLDB 10 Years Best Paper Award, and a 2016 Sigma Systems Award for his work on MonadDB. He's done outstanding service to the community, holding roles of General Chair of Sigma and CIDR, PC Co-Chair of VLDB and CIDR, and he has founded and leads the Linked Database Benchmark Council, which is a benchmarking organization for graph database management systems. So today, Peter will talk about string compression, but we have additional speakers, Mark Rasveld and Hannes Mühlheisen, who are also researchers at CWI, who will briefly, after Peter, talk about DuckDB, which is a new columnar system that is developed at CWI. With that, I want to thank Peter for joining us today.
Thanks, Annie, for this introduction. I'm overwhelmed. Yes, indeed, and I'm also very thankful that you made time for Hannes and Mark to talk about DuckDB. So today, though, we're going to go a bit low level. And I'm going to present this work we did on string compression, where we include Victor Leijs, who is now a professor in Jena, and Thomas Neumann, the creator of Hyper, who is, as we know, a professor at TU Munich. And well, this is hence it's actually a VLDB paper. It was in this year's VLDB, and but this year's VLDB, I mean, I was there, but the talks were not very well attended, and I think that this is interesting talk. So I'm kind of pushing it to when people ask me to speak now, I will talk about this because I think it's a very useful piece of software that came out of this, which is surprising because this is a piece of software that was created by only professors. That's also why it took quite a long time for this to finish, because we didn't have any PhD students working on this. So we actually did all the programming ourselves, which is a lot of fun. And the results of that you can see on this GitHub page. So if you go to GitHub CWIDA/FSST, you will find the code for the string compression, but also the replication package of that VLDB paper. Okay, so fast static symbol table. So it's about string compression. So let me briefly summarize kind of the state of the art in string compression in database systems. And strings in database systems are a very common phenomenon. It is probably the most used data type in database systems around, justifiably or not, actually, because you'll sometimes have people who store numbers and dates as varchars anyway. So there's lots of string content out there. So compressing the string content is useful. There are two main methods for doing so. One is dictionary compression, and the other one is general purpose compression. So dictionary compression, so the green stuff, you see a disk block where the idea is that you create a dictionary that holds all the unique values, the unique string values, And then the column, the string column, the values are actually represented then as small integers that refer to a position in this dictionary. And this approach, it works well if there are few unique strings, because if there are many unique strings, or if all the values are unique values, there are no duplicates, then this would not compress anything, of course. But in case there are many repetitions, then this dictionary D is much smaller than the original column would have been. Yeah, the other alternative, so if you do have lots of unique strings, then dictionary compression doesn't bring you so much. Then what people do a lot, and columnar stores do as well, is to apply what we call general purpose or even heavyweight compression. Despite the fact that these compression methods are optimized sometimes heavily, we still call them heavyweight. They're also block-based. So that means that they actually, they also, like these Lempel zip or entropy coders, they use some kind of symbol table, but it's not a static symbol table. It's like a hash table that contains pieces of string that repeat, but it's continuously changing. As you decode the string and as you encode the string, you're kind of building up this hash table by entering and removing information all the time. So it's highly dynamic, and that also means that you cannot really look at a compressed disk block and pick out an individual string, because you need to bring the hash table or the symbol table in a particular state, and you can only bring it into that state by actually replaying the whole decompression, if we talk about decoding. So that means that you have to do block-based decoding. So from a database point of view, and we are talking about kind of database string compression here, what that means is that if you have a disk block that contains snappy or LZ4 compressed data, then you have to scan, take a block, and really decompress that full block into some string heap. And now in the scan, it may happen that you're not interested necessarily in all the values, but you may have a predicate, some predicate, maybe on the string or maybe on something else, and you're filtering out much data. But that really doesn't help in the case of general purpose compression. You have to decode all the values anyway in order to get to even a single one of them. So that is a problem that heavyweight compression has. So FSST, which is the topic of this talk, fast static symbol table, it addresses two problems. The first problem, okay, is actually, if you look in the middle, the first problem is the problem that we have to decompress everything, okay? So the red stuff here. So if we do a scan, we always have to decompress all the strings. The second problem occurs when you look at the behavior of commonly used data structures in databases like hash tables. If you consider what's happening with strings in these data structures, then in the case of dictionaries, it looks pretty okay, because you can actually put the small integer codes inside a hash table. And so you do not necessarily have to decompress in the case of dictionary compression, as long as you remember where the dictionary D is. But in case of the heavyweight compression, you actually are forced to decompress strings, copy them into a heap, and maybe even into a separate memory area for the hash table. And the reason for that is that these general purpose compression methods do not allow random access for the reasons I explained. And hash tables are going to do random access. In fact, hash tables are just one example of data structures that enforce or force you to decompress everything and materialize the strings in uncompressed format. The same namely also holds for sort buffers. It also holds for shuffle operators. All these operators require random access or random writes or random reads to individual strings, and they force this materialization. So FSST is designed to address these problems that general purpose compression methods have for strings. So we want to be able to do a scan on a table with compressed strings and pick out individual values without having to decompress the column. And we also want a string compression method that can be used in random access data structures, such as hash tables, but also trees and sort buffers and shuffles. So that's what FSST does. So let me explain to you what is the main idea, which is a really simple idea on how FSST works. So a string in FSST is encoded as a sequence of bytes where each byte is a code. So if you compare this with dictionary, then one whole string is one code in a way. But here in FSST, a string of characters becomes a string of codes, multiple codes. Every code is a byte, and that byte refers to a symbol table. So for instance, the string http://in.toom.de is encoded in FSST as 063 because the 0 symbol in the symbol table is http://, the 6th symbol is in.toom, and the symbol number 3 is .de. So this symbol table is rather small. It only contains 254 values, in fact. And those values have a maximum length of only 8 bytes. And that 8-byte maximum length is chosen because that's the 64-bit word that CPUs currently support efficiently. So this is a relatively small data structure of only 2 kilobytes. If you serialize it on disk or on the network, it's even smaller because not all strings are 8-byte long. So then it's maybe half a kilobyte. So it's really a small data structure. And we only use 254 bytes. The 255th byte is an exception code. And this is to be able to encode strings for which there is no matching symbols. Okay, so that's a really simple escape mechanism where you have the byte 255 followed by the original byte that you cannot encode. And then you can still represent the string as an FSST string, even though in that case it will, for that character, be twice the original size. So we cannot have many exceptions, otherwise the compression ratio will go down. So this is a relatively simple representation for strings. And but the challenge here, a computational challenge or an algorithmic challenge, is what makes a good symbol table? So how do you find these symbol tables? And this is a hard problem. It looks like a simple problem, but there are many dependencies that make this very hard. One of our first approaches to come up with a symbol table was to say, okay, let's try to count all frequent substrings of a text, of the text that we want to compress, or maybe of a sample of the text that we want to compress. And you could use for that a smart data structure like a suffix array. And this indeed allows you to enumerate very quickly all the substrings of all possible lengths, well, at least from 0 to 8, quickly. And then, of course, for compression purposes, we are interested in those substrings with a lot of gain, where gain is defined by the length of the substring times the frequency of occurrence in your text. Because if you can encode many strings as long symbols, then you'll basically be replacing, for instance, 8 bytes by a single byte, which gives you a good compression factor of 8. So the longer and the more frequent your symbols are, the better for your compression. However, if you just take the top 254 symbols or substrings by gain, maybe from a suffix array, you get a very, very poor symbol table. The first problem is that frequent symbols overlap with other frequent symbols. So you will be basically overestimating the gain that your symbol table will be achieving, because one symbol will be eating up the actual frequency of occurrence of the other symbols. Because once you encode a substring with that symbol, then the other overlapping symbol will be that its actual frequency of encoding will go down. The second problem comes from the greedy encoding mechanism. So we actually use a greedy encoding mechanism, and that means that you will not necessarily consider, when you're encoding a string, you will not consider all positions, because the greedy encoding means that at a particular position, you will look for the best match, basically the longest symbol that matches at that position, and you'll just encode the text with that code, and then you move on, skipping over n characters, let's say, where n is the length of this symbol that you're encoding. So you'll be skipping, for instance, 5 bytes. That means that all the other symbols that could have started at position at the second position, at the third position, at the fourth position, you will not necessarily consider them. And the reason, by the way, why we're using greedy encoding is, well, we actually tried to frame this also as a full search, where we actually use dynamic programming to look at all possible ways to encode a substring, and not greedily. But this in fact in practice also doesn't improve the compression ratio much. So what we came up with for FSST is an evolutionary style algorithm that that considers this problem of constructing a symbol table kind of a generation like game, where you start with populations, and at every population you use the current symbol table on a sample or on the entire text to encode it, and from there you learn and you find candidates for the second generation, so you get a second population in the of symbols, and then this repeats. So every time you are improving the symbol table, you're encoding the text with it, you're gaining statistics on it, and that guides you towards choosing the population of the next generation. And that mechanism to find those statistics that you use to find those good candidate symbols are occurrence counts. So a very simple one is just counting how often each symbol is actually used when encoding a text. But also what you can do is you can count the occurrence of every 2 subsequent symbols. There are just 64K possibilities of subsequent symbols, so you can still build a pretty fast map or array that keeps track of these counts. And the idea is that you can create longer symbols from shorter symbols of the previous generation by concatenating them. And these subsequent symbol count statistics that you get give you a very good indication on how productive that would be, or what their actual frequency would be. Okay, so this is a very simple idea, and after just 5 generations, we did a lot of tuning, but we found that after just running this for 5 generations, you already find very good symbol tables. And it's basically by actually compressing the data with the symbol table and learning from that and using the statistics to find an even optimized symbol table. So this is one of an interesting result, but we really want to make this FSST method practical. And that means we want a good compression ratio, but we also want very high speed of compression and decompression. So if we consider the compression, which is the harder part of this, we want very fast compression. And the critical function for compressing strings is this greedy method, where you are looking at the string and you have to find the longest match. So you have to find the longest symbol in your symbol table that matches the next characters. So naively, we started with a naive approach where we would sort the strings in the symbol table lexicographically, and then you can do binary search on it. You can actually restrict this binary search with a small index on the first letter, and you restrict the range that you have to look through. But it's still a loop, and there are still branches in there. And our challenge was to make this encoding in a way such that we would not need even a loop or a branch. And what we came up with was a data structure that we call a lossy perfect hash table. So a perfect hash table is a hash table in which you have no collisions. And in a normal hash table, you always have collisions. There are perfect hash tables where you have an intricate data structure with multiple offset arrays that you can use to work out the collisions and make them non-colliding again. But these data structures are relatively slow, and this needs to work at a very, very high speed. So in fact, our hash table is a very simple hash table. But what we do is, if there is a collision, we throw out one of the two symbols. Which symbol do we throw out? Well, the symbol with least gain. But that also means, because we throw out a symbol, that we have room for one more symbol. And our bottom-up candidate generation mechanism can generate lots of candidates. So it effectively means that we will fill up the position in the symbol table with another candidate. It has slightly lower gain, but it's still a pretty good hash table. So the loss of the compression ratio due to this hash table is there, but it's very limited, less than 1%. So the way this works is that we have a hash table. This is this perfect hash table. It's based on the next 3 bytes. That's the key. So you can take the next 3 bytes, look it up in this hash table, and you will find something or you'll find nothing. And if you find nothing, then there is a second lookup table, which looks at the next 2 bytes. And this is called the short codes array. And that tells you whether there is a symbol of length 2 or 1. So you can actually, you first insert all the symbols of length 2 in this short codes array. And then in all the empty spaces, you can insert the single byte symbols in all the free slots for all the extensions of those single characters to 2 characters. So you insert them just in many positions, and then you can just handle this entire lookup mechanism by two lookups. One is in the perfect hash table and one in the short codes array that looks at respective 3 and the next 2 bytes. And the reason why we were so interested in doing a encoding routine that doesn't have a for loop and doesn't have a branch is because we wanted to implement this in SIMD. Okay, so modern processors have very wide SIMD, and Intel processors now have AVX 512, and they can work on many data items at the same time, but they do not support for loops, and they also do not support branches very well. But now we have a compression method that does not depend on any of these. And so what this, in fact, in order to make this efficient, what's effectively happening is that in a SIMD instruction, you have many lanes, and you can have many data items in execution independently in every lane. So this string compression method is like a meat grinder where you pull in a lot of string data, and the strings come out in parallel. So you're, for instance, like we are using 64 bits. So in 512-bit SIMD, you have 8 lanes, but then we unroll this loop. So we actually do it for 3 iterations in a row. So we have 24 strings that are being encoded in this loop in parallel. And in every iteration of this loop, we find one code. We do one greedy lookup. We find the next symbol for that string or an exception, and we emit that 24 at a time. So this loop, what it does, it has these expand, load, and compress store instructions. So if you're into SIMD, you may know that these are special instructions that were introduced in AVX 512 to detect if a lane is empty, so if it can take another job, and then fill it with new work, and compress store reverse if to retire work from a lane. And then inside of this, there are scatter and gather instructions. So the gather is the loading, so the reading. So you have 2 instructions that look into the hash table, and one gather instruction in shortcode. And every iteration you scatter one output because you write one code to the output. And in order to make this all work, the infrastructure around it is like it's a job queue. So you put in up to 512 or 512 job items, which are strings that you want to compress. So you should not call this routine with a single string. You should call it with a vector of strings, with multiple strings that you want to compress. If you have a very large string, it's actually chunked up. The routine does that for you. So you have independent work, and this independent work is pushed in through all these lanes in parallel. So that's a lot of low-level stuff, implementation. But in the end, it does achieve a very high speeds. But first, we tested this on a database workload. So what we did for this, I mean, we tested also in standard compression, on standard compression benchmarks. There is the Silesia benchmark, which is used a lot for in the compression community. So we tested also at that. But for databases, we also gather typical string columns from databases. So they are machine readable identifiers, human readable names, text, domain specific code, and also some good old TPCH data. And this corpus we dubbed the DB text corpus. It's also part of the GitHub that I mentioned at the start. And here you see a table with some example strings from these texts, and the compression ratio that FSST achieves and that LZ4 achieves. And we compare specifically with LZ4 because LZ4 is striking a very good balance between compression ratio and very high speed. So LZ4 is pretty fast, both in compression and decompression, and has a reasonably good compression factor. But FSST has a better compression factor. And if we look at the first bar, because now we look at not only compression factor in red, but also the speed for compression in green and the decompression speed in blue. And the first bar is the average overall the whole corpus, and the other bars are the individual files in the corpus. Then we see that the compression speed of FSST is actually higher than LZ4, and the decompression speed is equal to LZ4. So what that means is that FSST is a compression method that for database strings does not have any downsides over LZ4. And LZ4, by the way, is superior to Snappy in all the dimensions. LZ4 is faster than Snappy in both compression and decompression and has a better compression ratio than Snappy. But FSST, it doesn't have downside, but it has this upside, namely that you can actually do random access into a compressed string block. So you can have a block of compressed strings and pick out individual values. This is a benchmark that does so. So here you see just a scan operator where we make the scan actually decompress the values. So in LZ4, no matter how much data you actually select, because there is also a predicate in this experiment, a selection predicate that either selects almost no data or 100% of data. So if this predicate is very selective, so the 1%, then LZ4 is much slower than FSST, just because it has to do all this unnecessary compression on values that are not selected. And FSST, FSST here is actually decompressing the values, while if you use it to its full potential, the scan operator would not even decompress the values, because in FSST, a string, which is a sequence of bytes, sequence of characters, becomes a sequence of codes, and codes are also bytes. So in FSST, an original string, which is a sequence of bytes, becomes a sequence of bytes, which you can also consider a string, just a shorter string. So what that means is that it's relatively easy in FSST to keep strings compressed and delay compression. You can actually probably in your system use the same string data type that you already have in your database system and just leave the strings in their compressed form. So a scan could even choose to leave the data as is and pass them on to other query processing operators, like maybe an aggregation or a join. And that means that the strings will be shorter strings, and that maybe the hash table that's used in that aggregation or in that join will become smaller, and therefore it will become a faster join or an aggregation. So there are a lot of opportunities for doing for operating on compressed data, for doing lazy compression, for doing compressed execution. So in conclusion, we think that this is relevant work because there is a lot of data in databases that is string data. We had a paper in CIDR on white box compression, and we introduced a benchmark called the public BI benchmark. That was CIDR 2019, by the way. And this public BI benchmark also shows a lot of string data. And there was also this interesting paper from TU Munich in DB Test 2018 called the Get Real paper, which shows that there is a lot of string content out there. And string processing is a big bottleneck because strings are long, they take a lot of CPU time, take a lot of memory and disk. So compression is a good idea. And FSST provides this compression without downsides, with the upside of random access. So that's why I wanted to bring it to the attention of as many people as possible, because this is not only an idea in a paper, but it's actually also working open source software. You find the link here again, github.com/FSST. And I would really like to see people use this. And we for sure are going to integrate this as well in DuckDB in the future. So I think we should integrate this into real systems, because you get probably a compression factor on normally for strings of a factor 2 or 3, something between that, without real downsides. And that's the end of my presentation.
Okay, so maybe we should, before moving to the DuckDB presentation, we should get some questions. So I'll leave it to people. Please unmute yourself directly to ask questions about Peter's presentation.
Peter, Grant here, enjoyable talk. Could you say a few words about preserving collating sequence with your
you mean
FSST?
like, what do you mean with collating? Do you mean order?
Yes.
Well, that's impossible. That's provably impossible regrettably. You can try to do this, but it would go at the total detriment of compression ratio. So you can do equality comparisons on compressed strings, but you cannot do lexicographic string value comparisons without decompressing them. But while decompressing them is relatively fast, but you have to go decompress them for that.
I would have guessed you could have just had another matrix for your.
No, regrettably that goes ORI. I'm sorry. So you can try to do that. You can put the symbols in lexicographical order, but the problem is that prefixing symbols. But then if you would say, okay, I won't have any prefixing symbols in my symbol table, that will destroy your compression ratio. Regrettably.
More questions? So maybe I should ask a clarification question. So you suppose I'm in a column-oriented system, and I've got tuple with row ID 5.
Yeah.
Now that's in a block. Suppose I know that that's the 5th string in a block.
Yeah.
You're saying, so can I do random access to that too?
Yes, you can. Yes, you can. So in a
but the strings are, even like in an uncompressed form, they're different length, right? My strings are different length, so their compressed forms will be different length too.
Sure. Like in a columnar storage usually, but that's independent of like any string compression. The layout that you need for representing a string is a combination of a buffer with like the variable length content probably appended to each other, one after the other, and an array of offsets that points into this array, or lengths, but either one. You can, but that's the same if you actually do columnar compression on this offset array. You can do delta compression on it, and then you have lengths. You can even compress this further, but you basically have an offset array and you have a byte array. So it's the contents of the byte array that becomes smaller thanks to this compression method. The offset array will not shrink, other than the fact that the offsets will become smaller and you may need fewer bits to represent these offsets. But that is a factor. So if you have extremely small strings and the offset array is a relatively large part of your string representation, then the gains of this will be less. But well, very often if you compress this offset array, then you also need sub-byte for it typically. So then this overhead is not so big. It's the variable length heap that will shrink.
So the random access you're referring to are to random characters in there, or random components of a single string?
Yeah, if you want to go to string number 5, you would go to your offset array, and there at slot 4, I suppose, you will find an offset into this array. And then that array will contain a compressed string, and you do not need to decompress that string. And you can go to that string immediately. You can actually read the contents of this string immediately. Whereas if it would have been snappy or LZ4 compressed, you would first have to do a full decompress on the whole block. And that is not needed here. So you can pick out individual strings using this mechanism.
More questions. So we could probably take one more question, then leave.
So Peter, I have a very simple question.
Very good.
So when you do the compression, the compression preserves string boundaries, right? So if you have a string column, right, in a column store.
What is a string boundary?
Well, I mean, you have a column of strings.
Okay, yeah, you need to know this offset array. You need to know the lengths of the individual strings.
A single code is never going to represent sort of the end of one string and the beginning of the next. You will
well, usually, like, usually, thanks for the follow-up question, but usually it's a bit like what Semi just asked. So yes. in kind of string storage in a column store, yeah, you typically always store, or you have to store strings in 2 structures. One is an offset array, yeah, that tells you the starting points of the strings, and the second one is just a heap of bytes, and the offsets go into this heap of bytes. Right. And you can because they are typically stored contiguous, like the offset of the next string is the end of the previous string. Right. That's a very typical way of doing this. Right. But if a code represents part of one string and part of the next, like all your offset array can do is point to the codes are code. The codes are the bytes that you have in your variable area. Yes. Variable sized area. So those codes, so instead of the original bytes, which would be the ASCII characters, you now have codes there. And you need a symbol table to tell you, okay, what they expand to. But it's a sequence of codes, and you basically concatenate the symbols corresponding to all the codes that you see, and that's the way you decompress your string. Okay. Like this in.tum.de example I had, which was encoded as 063, which is the concatenation of the symbols 0, 6, and 3. Right.
But each string within a column will be essentially encoded separately, right?
Each string in a column will be encoded separately, yes.
Yeah, that's.
I think that's what Ken was asking.
Yeah.
Okay. Yeah, but you can even point into a string halfway in a way now with something that would also not be possible in a snappy encoded or LZ4 encoded block.
So let me preempt you. I have a feeling you're about to ask a question, but we got maybe 20 minutes left. So let's give the next Mark and Hannes some time. And if we've got time left, then you can ask both Peter and Mark and Hannes any of them questions. Okay, so so Peter, can you stop sharing your screen? I'm assuming Mark or Hannes will want to share their screen.
Yeah, I will share. Is it already sharing now?
Yes, you can see it, but it's in it's not in presentation mode. So
now?
Great. Okay, so good to go. Thanks, Mark.
All right, so, well, I guess I'll just start, right? Thanks for having me. Thanks for the invitation. My name is Mark. I'm a PhD student at the CWI, and I will give
You're a postdoc.
I'm a postdoc at CWI. Sorry, old habits die hard. I'm a postdoc at CWI, and for the last 2-ish years, I've been working on DuckDB together with Hannes and other people at CWI as well, but primarily the 2 of us. So I would do kind of like a short, lightning-ish talk about this, maybe like 10-ish minutes, and then we can see what time we have for questions. So really short motivation. I don't know how many of you saw my CIDR talk. Basically, DuckDB is kind of geared towards data scientists. And we kind of saw this observation that data scientists, well, they work with data. Our field, database research, we've been spending over 50 years perfecting database management systems. So obviously they should be using database management systems, right? But the truth is that it's unfortunately not always the case. So here's a quote by Hadley Wickham. If your data fits in memory, there is no advantage to putting it in a database system. It will only be slower and more frustrating. So for those that don't know, Hadley Wickham, he's kind of one of the lead R guys. He made ggplot. He works in RStudio. He's one of the kind of the big guys in this data science community. And he basically tells us that, hey, your work sucks, right? Like databases suck. And as a database researcher, that offends me deeply. But you know, maybe they just don't need databases, right? If you don't need a database, then why would you use one? So let's have a small look at what all these people are using. Well, in Python, if you look at the most popular libraries in the data science community, it's NumPy and Pandas, which are kind of data wrangling libraries. I assume most of you are vaguely familiar at least with them. Then you have Matplotlib, which is like a plotting. And then you have like a long tail of a bunch of analysis, classification, ML libraries, SciPy, TensorFlow, etc. This is from 2018. I guess now it's been like changing a bit. Maybe TensorFlow is a bit higher up. But I think NumPy, Pandas, they're still very widely used. In R, it's kind of quite similar. Sorry? Oh. In R, it's kind of quite similar. You have Rlang and RCP on the top, which are not actually used by people, but they're used by packages, like a kind of a developer package. So they're not very interesting. But for the rest, you again have these data wrangling libraries. You have dplyr, Tibble, data.table. You have plotting library, and then you have a bunch of like analysis classification libraries. All right, so what do all these data wrangling libraries have in common? What do Pandas, NumPy, etc. have in common? Well, they perform database operations. They do joins, they do aggregations, they do filters, projections, basic data transformations, etc. So it's kind of clear that data scientists, they do kind of need this database functionality, but they're not using databases to provide that. Instead, they're kind of like reinventing database systems, and they're not doing a very good job at it. They're kind of like ignoring all of the work, all of the hard work that our community has put into database systems, and just kind of, yeah, creating kind of borked clones of these database systems. They don't have optimizers, they materialize all the intermediates, they don't support out-of-memory computation, most of these don't support parallelism, scalability, etc. So they have all these issues that database systems have already, database researchers have already solved quite some time ago. They can do all these things and much more. However, according to Hadley, database systems, they're slow and frustrating. But, well, we don't think they need to be slow and frustrating. We think they can be much nicer. So in DuckDB, which we pegged as the SQLite for analytics, because we really like SQLite. So DuckDB, it's a database system focused primarily on analytical processing. And our core features are that we have very simple installation. We have zero dependencies. It's supposed to be, it's integrated into package managers of Python and R. It's an embedded system, just like SQLite. So you don't have any client server management. You can directly start using the system from within your shell. We have a single file storage format. And yeah, we're focused on analytical processing, so column store, etc. I'll go a bit more into that later, now I guess. So this is kind of at a glance, the internals of DuckDB. It's a column store database, which, well, I guess everyone here knows what that means. It uses vectorized processing, kind of like a vector volcano model, very similar to what Vectorwise used. It has an art index, mostly for primary unique key constraints. These types of indexes are not super useful for analytical workloads. It's mostly just for constraint enforcement. And then we have MVCC, kind of an implementation of the hyper MVCC algorithm, if you guys are familiar with that, but optimized for analytics. We have a single file storage format. It's written in C++, and we use a modified version of the Postgres parser because it's a pretty damn robust parser. It's been a very good decision to use that one. Yeah, DuckDB uses a very typical pipeline for query processing. We take a SQL string, parse it, create a statement out of it, do some binding, planning, create an optimized logical query plan, run optimizes on it to create an optimized logical query plan, run a physical planner, and then create a physical plan, which we then execute using this vector volcano model. We have a morsel-driven parallelism model, similar to Hyper as well, where pipelines are constructed at pipeline breakers. So pipeline breakers, for example, are join hash table builds, aggregates, or order by clauses. And each of these pipelines are individually executed, and the scans are dynamically consumed by multiple worker threads. So these scans are kind of, they're not upfront scheduled and said like, okay, this thread executes the first 10% of this table, this thread executes the next 10%. They're kind of like dynamically consumed to do load balancing. And the pipelines have like dependencies in between them. So for example, this is query 3 from TPCH, I believe. Here you have 3 pipelines, actually 4 pipelines, but 3 important pipelines. First off, you have 2 hash table constructions on the right. You have the customer hash table construction of the join. You have the orders hash table construction on the join. Those are P1 and P2 there. Then you have kind of this big pipeline that scans the line item table, probes the 2 hash tables that's created for the joins, and does this aggregate on the group by. Then you have one more pipeline on the end actually that scans this aggregate hash table again and does the top n. Well, this one's kind of small, not very performance critical in this query. But the 3 main pipelines are down there, and they're all doing like parallel scan partition division using this like this model. One nice thing that we support is that we support scans of many different sources of different file types, like our native storage, obviously, but also from Parquet, CSV files, but also from in-memory types. And this is kind of a big advantage of running as an embedded system, is that we are directly in memory next to the Python client, next to the whatever is in memory of this data science tool, right? So we can directly scan Pandas data frames, R data frames, Arrow, basically what have you. And often we can do these scans for 0 cost for numerics. For strings, it's a bit more complicated, but we can scan integers, doubles, etc. Without having to pay any conversion cost. We can just like kind of set up a pointer into that data frame and like just read it. And these scans can also be parallelized, which is of course nice because you can basically unload you can use the entire parallel execution engine on these different data formats. And we can also write to these formats. So you can even use the DuckDB execution engine to go from a Parquet file, go through the execution file and output a CSV file or output a Pandas data frame, whatever. And this is nice for these kind of ML-ish workloads where you have to do data wrangling from one type to often another type. It's kind of like a component in this in these pipelines, because often you have to go through to a different library that then accepts maybe a Pandas data frame and what have you. You can do all of this in one go, basically, without having to pay for this conversion separately. We have a composable interface. So this is our Python interface. We also support full SQL, of course, but for Python users, it's usually not that nice to use SQL, depending on what you're doing, because composing SQL can be a bit annoying, and especially debugging SQL in like an interactive way can be a bit annoying. So we have this alternative interface, which is kind of directly built upon our logical tree, where we can create like scan nodes, filter nodes, joins, and aggregates. And in this this interface, so for example, here you can open a database system, create a table scan using like db.table. Then you can push a filter on top of that, db.filter. And the nice thing is any of these nodes you can combine again, you can print, so you can like inspect intermediates. So if you do like, for example, here you have a scan followed by a filter, you can do this .show and it will basically push a limit and then print it, which will basically print like a snapshot of what is in there to kind of get a feel for it. And then you can do like an aggregation on top of that, etc. It's nice for kind of interacting with the data. And also here you can combine data from different sources like CSV files, Parquet, Pandas, etc. Join them together, what have you, do unions, etc. Yeah, so one of our goals as well with DuckDB was easy extensibility. So of course we are also a research institute, and we also want to like sometimes prototype ideas or try them. And it's nice to do that in an actual system, because you get more of a feel of how will this actually work in the real world, rather than how is this going to work on like my one prototype that might not actually be representative. You also usually get brownie points from reviewers for implementing something in a real system, so that's also good. So this was one of our goals as well. And we think it's quite successful. Some people in our group are using it for that purpose as well. It's easy to compile, no dependencies. Allegedly, the code is pretty readable. I've heard from other people. I can't, for me, obviously it's pretty readable because I wrote a large part of it, but other people allegedly think so as well. And it's pretty easy to add new operators, functions. You can change the grammar quite easily, etc. So for you guys as research, that might be interesting to use DuckDB for that as well, if you are so inclined. All right, so DuckDB, free and open source. It's currently in pre-release version 0.2.3, I think, since a few days ago. We have a website, we have source code, MIT license. Feel free to try it. Feel free to take whatever you want from it. If you break it, please open an issue so we can fix it. And yeah, I guess that is more or less it. Thank you for having me. And any questions?
Thank you, Mark. So I think, at least within my group, we are working with DuckDB, and they could also confirm the readability is it's easy to read.
Very good.
And we do look at it even so for GraphFlow, which is not on DuckDB, but we still do look at how certain things have been implemented in DuckDB, because a lot of we see a lot of sort of ideas from Hyper, for example, for which we don't know, like Morsel-driven parallelism, like, you know, we don't know how it's been implemented. We can look at DuckDB and see how it's been implemented. So it's been also good, I think, for the community to have reference implementation of some of the state-of-the-art ideas in relational system, I think, relational systems. Anyway, so I'll open up, you got about 5 minutes. I'll open it up to questions to Mark. And also feel free to ask, I think, questions to Peter as well for the first part of the talk.
Hi, I have one question to Mark. Hello?
Go ahead.
Oh, okay, okay, listen to me. So I'm just wondering, like, if you use DuckDB, so, and I've been using, say, Pandas for last 3 years. So I don't have to use Pandas anymore. I can just write my queries and analytics through DuckDB and the API you have provided.
Yeah, so that is more or less the idea. Of course, there are some parts of Pandas that we probably don't support yet. I'm not sure. Pandas has been around for a while. It probably has some exotic things. But one of our goals as well is that you can kind of incrementally start using it. So you can just read a CSV file, do some pre-processing DuckDB, and then if you have to do something in Pandas, because they may have some kind of edge case functionality that we don't have, you can just convert to a Pandas data frame and do that anyway. And one thing is, I have to say, our CSV reader is very good. I'm very happy, very proud about that. It was implemented by Til Duren, and it's very fast and also automatically figures out things about the CSV, which the Pandas CSV reader is not. So that is already one very nice reason to use DuckDB, I think, is even if you just use it to read a CSV, it already simplifies your life a lot over using the Pandas CSV reader.
I see, and just a quick question on top of that, like you said that it's a single file build, like all in C++, right? It's C++11. You made all.
It's C++11.
Why not C or any other functional languages you used?
So why not C? I think C is at this point rather dated. It's of course most systems have been implemented in C, but I think C++ is just a lot easier. You have a big standard library. You have exceptions that just make code more readable. You have smart pointers, smart locks, etc. That means you don't have to worry as much on about all these different things while still getting basically the same performance you would get in C. I think the other language we debated on was Rust, of course, but we ended up going with C++ partly because of our own familiarity, and also because C++, of course, much more mature and ties in much easier with other languages. And as an embedded database, that's quite important because you want to run within Python. Now, Python is written in C, or CPython is written in C at least. R is written in C, etc. And a C++ library ties in completely naturally to that, whereas a Rust library does not. So that was our main reason for choosing C++.
Okay, thanks.
Any other questions?
So I had a quick question. On the use of vectorization, you rely on the compiler to actually emit the vectorized aspects of it. Is there some kind of cost analysis that you did in terms of actually writing or using intrinsic functions versus how much benefit you would get, or is it just the way it is right now?
But this is kind of difficult to say because it very much.
No, this is a misunderstanding. So this is different uses of the word vectorization.
Yeah.
So with vectorization, we do not necessarily mean SIMD execution. Vectorized execution is an execution model in which you operate on batches of columnar data, which is, by the way, very amenable to SIMD execution, but it's not vectorization in the auto-vectorization sense of a compiler.
Yeah. This is maybe a misnomer. It's indeed in our world, vectorization means that. But I can also answer your question on SIMD because it is kind of related. So we have done some experiments looking into intrinsics versus non-intrinsics. And the thing is, it really depends on what. For very simple functions, like, I don't know, you have a loop that adds some numbers, the compiler will basically catch these cases. For others, like a bit more complex string operations, etc., intrinsics pay off. We don't have any intrinsics in our system yet. Mostly also for portability, because of course we have straight C++ code. It's going to work basically everywhere. If you use Intel intrinsics, it stops working everywhere. So, and that's one very important aspect of our system as well, is that we want it to run everywhere. We want it to run on the new MacBooks as well, right? But we are not like completely opposed to it, and we have been thinking about some ways of adding these intrinsics for operations where it really makes a big difference. But again, like we will do that kind of with care, you know, only if we can show that it makes a very big performance difference to do that, rather than just letting the compiler do it.
Okay, thanks.
We could take one last question if there's any.
I have a question.
We'll take one more question. Okay, last question.
Do you have a performance comparison between pandas like join and DuckDB join?
I don't think we have run that with pandas yet. I mean, it kind of depends, I think, because also we have a parallel join, so you can get any speed up over pandas, of course. I think, yeah, probably we're faster, but I haven't run this comparison.
So maybe I'll squeeze in one final question. So you claim to be SQLite. How do you measure how light you are? Like, what is your metric of, like, what's your goal when you're developing DuckDB to be light? And what is light for you?
Well, light, I think we claim to be SQLite in because of certain aspects, maybe not necessarily because it's super light. I mean, we are trying to make an analytical database system, which necessarily also implies that we have kind of a rich SQL dialect. We have a lot of analytical functions and such. We have like window functions. We have like a lot of functions that SQLite might not have, right? Like SQLite is kind of a bare bones OLTP style system. So I think in terms of lightness, we try to be pretty light in terms of code, but we can never match SQLite because we just try to do more things. I think the way we try to be SQLite is more that we follow a lot of their philosophies. Like we have a single file compilation build where you have like duckdb.cpp, duckdb.hpp, that's the entire database system. We have a single file storage format. We have a dependency-free system, so there's no external dependencies that you have to link to, and no like difficulty with setting this up or integrating this into your project. And also that we are very focused on testing and correctness. So we have like a very large test suite as well to make sure that everything kind of works as expected, let's say.
Okay, great. So let's end here. Thank you very much to Peter and Mark, and also Hannes for joining us.